So now let us consider the SN1 reaction. So SN1 stands for the substitution nucleophilic unimolecular reaction. Here it is, I am going to consider the hydrolysis of tertiary butyl bromide. So this is the best well-known example. We are going to hydrolyze that particular molecule in presence of water. So you can see that here, the whole molecule is same. This is the reactant, this is water molecule, and this is product, and this is a byproduct. Okay. So in the reactant or in the product, you can see that only the difference is that the bromine is replaced by the OH. So here it is, the Br is substituted by the OH ion. You can see that. We can say that. From this reaction, we can easily say that this particular bromine is going to be replaced by the hydroxy OH ion. So this is a kind of substitution reaction. Okay. So now let us consider its kinetic mechanism. While studying substitution reaction, the first thing that we must know about their chemical kinetics. So according to the kinetic study, the rate of this reaction is directly proportional to the concentration of substrate. So here it is, the substrate is tertiary butyl bromide, right? Substrate is tertiary butyl bromide. So the rate of reaction is directly proportional to the concentration of this tertiary butyl bromide. So the square bracket represents always concentration of that particular species molecule. So now we are going to remove that constant of proportionality. So the K is there, and that is the rate constant. Okay. From this rate, we can easily say that the rate of reaction depends only on the concentration of reactant, that means tertiary butyl bromide. Hence, in the slow state, only the concentration of reactant is going to be involved. Therefore, the reaction is unimolecular reaction. The reaction is unimolecular reaction. Okay, this is the basic kinetic study of this reaction. And it is very important. We can easily identify whether the reaction is unimolecular, bimolecular, what is the rate of reaction, and what type of species should be involved in the rate reaction. Okay. Now next one is, so let us understand the mechanism of this reaction. Okay. The first step is the cleavage of CBr bond. That is CBr bond. Why we are going to consider CBr bond? Because bromine is the living group, and that particular carbon is a reaction center. So CBr bond is slowly broken down to form the carbocation intermediate. The step first is the returning step according to this. So why that particular bromine is going to be eliminated? Because bromine is a large group, bulky group, and after the removal of this bromine group, a tertiary carbocation is formed. So the tertiary carbocation is more stable species. So whatever the intermediate form in this reaction, that is carbocation, that can be stabilized by the presence of these three methyl. So therefore, the departure of bromine is taking place without any driving force, because the driving force is the formation of this carbocation. And now this step is known as rate determining step. Why rate determining step? And how the rate of reaction is determined. So the first, we must always remember that the bond breaking between the leaving group and the alpha carbon atom. In any kind of reaction, if you look at this step, the bond between the leaving group and the alpha carbon is going to be broken down. That means this state belongs to the slow state. And so here it is, you can see that this is bromine is leaving group and this is alpha carbon atom. So this bond is going to be clear. CBr bond is going to be clear. That means this step is always slow state, and from the slow state, the rate of reaction is determined. That's why it is known as RDS step, right? So RDS means rate determining step. In the next step, the rapid reaction between the carbocation intermediate, whatever the intermediate form in this first step, that is going to be reacted with the nucleophile, just like as water molecule. We are going to hydrolyze that molecule. So we are going to react with the water molecule. So here it is. This particular molecule is planar molecule. You can see here that in the starting case, this is sp3 hybridized molecule. When the bromine group is depart with the pair of electrons, the intermediate form is a planar molecule. So all these three methyl groups lie on the same plane. So therefore, the nucleophile, in the next step, the nucleophile has a possibility to attack either both the faces, from front side or back side. The nucleophile has equal chances to attack on this carbocation from front side or back side. So now you can see here. So when the nucleophile is going to be attacked from this back side, okay, here it is. The dotted line indicates that this particular methyl group away from the observer or behind the plane of paper, and this thick line always indicate that this particular group is towards the observer or above the plane. So if this particular water molecule is going to be attacked from the back side, then the product will be like this. And if this particular nucleophile is going to be attacked from the front side, which front side means the side, the same side at which the leaving group is going to be deeper. Okay, so here it is. You can see that here it is. So these are the two products formed due to the planar geometry of this intermediate, and the nucleophile has equal chances to attack either both sides. Okay, so the next one is step 3. So the rapid deprotonation of the produced neutral final product. Whatever the product is going to be formed in the last step, there is a rapid deprotonation. So you can see here. You can see here. This water molecule is going to be extract this proton, and it deprotonate that the final products. Similarly, in the second case also. So these are the final tertiary butyl alcohol products, and this is a very fast step. Attack of nucleophile aldehydes occurs in a fast step, and the bond breaking aldehydes occurs in a slow step. Okay, so these are the products, two products possible in this case because of the planarity of the intermediate. Okay, either the nucleophile that attacking species can attacks from both sides, either top side, bottom side, or we can say front sides, back sides. Okay, so the next one is the energy profile diagram for this reaction. So here it is. You can see that this particular reaction having two-step reaction. So most of the energy profile diagram always says the number of steps possible in the reaction. Here you can see that there are two humps, right? It means the reaction having two steps. The first step is, this step is nothing but the formation of, or this is the transition step. It involves the bond cleavage, the CBr bond cleavage, right? And this particular point indicate the formation of intermediate, right? And this is the second step is always indicate the attack of nucleophile. So the first hump indicates the bond cleavage, CBr bond cleavage. Second hump indicates the attack of nucleophile on that particular carbocation. And finally, the product is going to be. So the SN1 reaction always have two humps because of it is a two-step reaction. So energy profile diagram indicates number of steps possible in the reaction. Okay. Now this is related with the SN1 reaction. So we are going to consider the second, that is SN2 reaction. SN2 means that S stands for the substitution, N stands for again nucleophile, and that 2 is nothing but the biomolecular reaction. In the earlier case, SN1 reaction represents the substitution nucleophilic unimolecular reaction. So, okay. Now let us consider the example. A general example we are going to discuss here. This is a molecule having a tetrahedral carbon. You can see here all the groups are alkyl groups. R groups are different. R1, R2, R3. This X is nothing but the living group. It may be halogen. It may be another type of groups, but it is a living group. Okay. So now here it is. You can see that the nucleophile is going to be attacked here. Similarly, that and it departs the living group. So the final product is along with the nucleophile, and here it is living group. Okay. So chemical kinetics. According to the chemical kinetics, for this reaction, SN2 reaction, it tells that the rate of reaction is directly proportional to the product of concentration of substrate and the concentration of reagent. So here it is, you can see that this is a substrate and this is a reagent. So in this case, the rate is directly proportional to the product of concentration of this substrate and this nucleophile is also. So now you can write here it is where okay, substrate is going to be changed. Okay, it's my mistake. The substrate is going to be changed. The substrate should be like this. All the R groups are different. It is not a tertiary carbon. It may be secondary or primary halide. Okay, and the nucleophile. The final product is the final. Sorry, we are going to remove that constant of proportionality. And then we are going to insert this constant known as a rate constant. Okay, so from this kinetics, we can easily say that the rate of this reaction depend upon the concentration of reactant and reagent. Okay, it means in the slow state, the concentration of reactant as well as the concentration of product is going to be concentration of reactant as well as reactant is going to be more. From this, we can easily say that in the slow state, the concentration of reactant is also important and the concentration of nucleophile is also important. Hence, in the slow state, there are two species involved, right? So it means the reaction is bimolecular. In the previous case, while in case of SN2 reaction, in the slow step, only the concentration of reactant means only one species is involved. That's why it is unimolecular. Here it is in the slow state, the concentration of reactant as well as reagent is going to be involved. So it means two species are involved. So we can call as a bimolecular. Now let us understand the mechanism. Here it is, you can consider that the nucleophile is going to be attacked on the reactant side. And this type of transition state is going to be formed. What happening when the nucleophile is going to be attacked here, at the same time that particular leaving group is going to be departed. When in case of SN1 reaction, initially leaving group is going to be departed. That leaving group is going to be departed, and then after that formation of carbon cation nucleophile unit. But here the nucleophile initially attack and then leaving group departs. So this type of process is known as there is a bond making, and here it is a bond breaking. So it is a concerted process. The bond making and bond breaking takes place is known as concerted process. So here it is a partial bond between this carbon and nucleophile is there. A new bond is going to be formed, while this bond is going to be break. CX bond is going to be clear. The bond between the leaving group and alpha carbon is going to be clear. So this dotted line indicates the partial bond formation and partial bond cleavage. So this is known as transition. While after that the transition state is collapsed, the product is going to be formed like this. You can see here the nucleophile is here. And one more thing is that that particular nucleophile is going to be attacked from the back side of the leaving group, not from the front side. It is not going to be attacked from the front side. Okay, so it is going to be attacked from the back side of the nucleophile. So this particular carbon, you can see that the configuration is going to be inverted. Electrophilic carbon has inverted. Here it is. You can see that leaving group is on the left hand side, while in the product case, that incoming nucleophile group is in the right hand side. Okay, so okay, here it is. You can see that. So this is an X group, that is the leaving, right? The incoming group is also negatively charged species, nucleophile as it is a electron rich species as we discussed earlier. And that leaving group is also electron rich species. It differs with the pair of electrons, right? So both are the negatively charged species. Therefore, the attack of nucleophile from the same side of the leaving group is not possible. Because of this, the attack is blocked from the front side because both the species are electron rich species, right? So that's why the attack is blocked. While from the back side, there is no hindrance for the nucleophile because the leaving group is far away from this. Therefore, the backside attack is easily possible and therefore the leaving group departs with the pair of electrons. So this attack is easily possible as compared to this, because in this case, both the groups, departing group, leaving group, and an incoming group, that is nucleophile, both having negatively charged species, so they repel each other. Therefore, the attack is impossible. While in case of backside attack, there is no such type of hindrance, so the backside attack is easily possible. You can see here. Now here it is. This is your substrate, and that is incoming nucleophile. It is attacked from the backside, and this green bond, just like as a leaving group, departs with the pair. So this is the SN2 type of reaction. Okay. Now we are going to consider the energy profile. Here it is. You can see that this methyl chloride is going to be reacted with the hydrolysis of methyl chloride is there, right? So you can see that this is the single hump, right? While in case of SN1 reaction, there are two humps. It means SN2 reaction is a single step reaction, while SN1 reaction is a two-step reaction, right? This is a transition state, as we discussed earlier. When this transition state is going to be collapsed, that particular intermediate is going to be converted into the product. And here it is, you can see that the reactant has highest energy as compared to the product. So now today we are going to discuss only this topic, and today I will stop here. Okay. So yes, anybody having questions? Yes. Yes. Hello. Is there any question? Is there any question? Hello. You can talk now.